So, is it okay if I start now? So, I'll start. Hi, guys. Amogh Jahagirdar here from Mumbai. And today we're going to talk about learning ML with Kaggle. So, let's begin. So, let's get started. So, the talk will be distributed into mostly three parts, but of varying durations. First will be an introduction. Second will be a rationale as to why Kaggle essentially, and third will be a bit more interesting than the other two, in which we will take up a competition, analyze its data, go through the various patterns in the data, uh, choose uh, choose different machine learning models, apply them, choose which is best, then apply further more advanced modeling techniques like voting based ensembles, and then sub create entire create predictions for our challenge and submit them to Kaggle and make our first prediction essentially. So I'll walk you through each aspect step by step. If you have any doubts or queries, you can just comment on the YouTube live chat. All right. So let's begin. Basically, an introduction. Introduction. I'm Amogh. As I said, I'm a third year student in NIT Trichy, and I've been doing machine learning for the past 1.5, 2 years. Also, apart from machine learning, I develop Flutter apps. I was developing React Native and Android apps, and that's about it. I study in NIT Trichy, and uh, so this is my for my introduction. This is my profile page on Kaggle. Uh, my user handle is Amogh J Rules, and I'm ranked in the close to top 500 in the kernels category. I'll explain to you what that means in just a bit when I talk about Kaggle. All right. So moving forward with Kaggle, why Kaggle? So before that, let me explain to you what Kaggle is. So Kaggle essentially is a competitive machine learning platform where people uh, there are competitions which are hosted under the compete section, and there are different competitions. This one is regarding NLP. There are ion switching. It's something to do with signal processing. A lot of image classification challenges and regression, all kinds of stuff, like everything related to machine learning. Essentially, there's a competition for that, and these competitions are hosted by big organizations like Google, sometimes Flipkart, Amazon, AWS, all sorts of things, and they give huge prizes. And there's a huge community that is based around these competitions where a lot of data is shared. They make custom data sets and share them. So currently, they are running this COVID challenge in which you have to forecast the growth of the COVID pandemic, which is going on right now, and a lot of other data sets also, just for you to play around. There's a notebook section where people write their analysis. We're going to be analyzing our challenge in a Kaggle notebook as well, so you'll understand more about what I'm saying. Next, there is a discuss section where people ask doubts, discuss ideas for getting a better score at the competition, and so on. And there's finally a courses section where there are basically data science education with different levels and different categories of data science. So that's essentially Kaggle. And why Kaggle? So I personally, I'm a very goal oriented learner, as in I mean that whenever I have a certain goal in front of me, like a certain target, I can analyze things better, and I can get a hold of them better, more hands on approach, if you say. So why Kaggle is in there is, when you have a competition, there is a challenge in front of you. There are thousands of people competing with you, and see the leaderboard here is like very close competition, as you can see here. So it gives you a motivation that so many people are working on the same problem. You can learn from them, you can compete with them. It motivates you to see that if you are doing well, it gives you a sort of pride, as in why you're doing well. Apart from that, there are the data sets, as I said, are amazing. The notebooks, there is a lot to learn from notebooks. Like, I don't think uh, one can learn it even entire year if you spend on Kaggle. There is still always more to learn. Not only Kaggle, like machine learning itself is such a uh, like a big topic. It has so many subtopics like computer vision, AI, reinforcement learning, natural language processing. So I think Kaggle gives you a sort of all-round approach, all-round resources, if you say, to doing stuff like that. So that's about why Kaggle. So now, as I said, we'll move on to the interesting part of our topic, which is the Titanic challenge. So it's a very famous competition on Kaggle, and it's the competition that beginners usually approach. And it's basically a little dumbed down for everybody, and to make beginners friendly with and get started with Kaggle. So this is the Titanic machine learning from disaster challenge. Let me explain to you the problem statement. So you are given a data set of the passengers on Titanic and their details, like their name, gender, their family size, uh, stuff like that. We'll go through the data in more detail. And essentially, what you have to do is you have to do a binary classification and predict if given a certain passenger ID and passenger name, will this how likely is this passenger going to survive after the Titanic crashed? As you know, like the Titanic is one of the most famous historical crashes of shipwrecks, and there was a movie also based on that. Most of you guys must have seen it, I guess. So okay, so this is an overview of how Cal competition work. Join the competition, get to work, which we'll be doing in a bit. Make a submission, check your leaderboard, and reiterate. Improve your score, learn from other people, and stuff like that. All right, so let's take a look at the data which is available here. So, an overview of the data. The data has been split into two groups: a training set in train.csv file and a test set in the test.csv file. So the training set essentially has the labels, the correct labels, the target values which are there for each passenger, and it has a bunch of features like passengers' gender and the class, whether you're traveling in first class, second class, and stuff like that. And the test set essentially has similar features as the training set, but only the let me just zoom in a little bit. So it has the same features, but it doesn't have the labels, the correct labels, and we have to predict them. So let's go through the data dictionary and understand what each variable is like. So there is a variable called survival that refers to whether the passenger survived after the crash or not. A 0 in that column means no, that passenger did not, whereas a 1 means yes, that passenger did survive. P class means the ticket class. 1 is first class, 2 is second class, and 3 is third class. Sex, it is the key is male and female. Age is the age in years. Sib SP is the number of siblings or spouses this particular passenger had on the Titanic. PARCH is the number of parents or children that the person had on the Titanic. The ticket number refers to the ticket number. It's not very useful as a sort of information, but it's still there. Fare is the amount the person paid, the passenger paid to get onto the Titanic. The cabin number is the room number for the person who, like the where he was staying on the Titanic. And embarked is the port of embarkation. There are three categories: Cherbourg, Queenstown, and Southampton. All right. So there is a further notes, but I don't think we'll need that. We can straight on move to the notebook. So let me just open it here. All right. So the Titanic challenge. Here we go. So let me just hide this. All right. Why is it not going down? All right. Let's zoom. All right. So what I'll be doing here is this is a notebook, is a live Python notebook, and I have written a bunch of code already, and along with a few notes.
நான் ஃபர்ஸ்ட் வெபினார் அட்டெண்ட் பண்றதுக்கு ஒரு 200 வாலட் பாயிண்ட்ஸ் வாங்கி வச்சிருந்தேன்டா. காசு கொடுத்து எவ்வளவு கொடுத்து? 200 ரூபாய் கொடுத்து. பைத்தன் வெபினார் பைத்தன் சொல்லி தருவாங்க. இப்ப கூட இருக்குது. பைத்தன் ஜாவா எல்லாமே இதுலயே சொல்லி தருவாங்க.
ஹலோ.
அது பண்றதுக்கு அப்படியே 5 கிளாஸ் தான் அட்டெண்ட் பண்ணேன்.
Please mute your personal mics.
என்ன வெபினார் வணக்கம். GUVi எப்படி கொடுக்குறாங்க?
Can you mute yourself? Yeah, thank you. Okay, so the problem statement once again. So the sinking of the Titanic. Yeah. So what I was saying was the notebook. This is a live Python notebook. I've written a bunch of code, and we'll be running these cells one by one, seeing what is happening after I run that particular code. And then we'll be understanding what each line does and trying to make the best prediction we can. Is somebody? Yeah, please mute your mic. Yeah, thank you. So let's begin. Cool. The Titanic challenge. The sinking of the Titanic is one of the most infamous shipwrecks of history. The Titanic sank after colliding with an iceberg, killing 1,502 out of 2,224 passengers and crew. So, yeah. So, contents of the notebook. So first, we'll divide this entire session into 4 parts. First part will be exploratory data analysis. This is a kind of technical term, but essentially what it means is that we'll be analyzing the features, going through them one by one, finding any patterns or any hidden patterns which are not visible straight away, but by plotting a few graphs or a few certain other plots, we can understand these relations between different features and relation to the final dependent feature, which is the target. The next part will consist of feature engineering and data cleaning. So what feature engineering means essentially is that maybe in some cases the features which are given may not cannot be used directly. Like suppose there is a column in this data set which is called title, which is basically Mr., Mrs., Mademoiselle, stuff like that. And this doesn't make much sense to a machine learning model because it doesn't have the human understanding of what Mr. means or what Mrs. means or what Miss means. It doesn't have the contextual information. So what we do is we convert them in a form so that the machine learning model can make some correlation between different other parameters in the model. So that's that. And data cleaning refers to like clear in case of strings, stripping off URL links, stripping off punctuation marks which don't make sense to the model, and also if we are missing some values in some columns. So rather than dropping those columns or rows, we can fill them with, say, the mean of the entire row or mean of the entire column in order to not waste data. So that's what data cleaning is. Then we'll move on to predictive modeling. The entire data set which we have made essentially with features and data cleaning and stuff, we'll be running them through a bunch of machine learning models provided by scikit-learn, and then we'll be applying more advanced cross-validation algorithms, ensembling, and we'll be analyzing what important features which are the most important features and rank them according to their importance. Lastly, we'll be compiling our results into a .csv file again, but this will be in form of a submission wherein we'll only have a passenger ID and 1 or 0 for the survival prediction, our survival prediction, and we'll submit it to the Kaggle leaderboard and we'll see how well we do. All right. So I guess all of us are on the same page now, and we'll begin now. So part one, the EDA. So let me just import all these libraries: NumPy, Pandas, Matplotlib for our graphs, Matplotlib and C1 for our graphs, and just define some initial styles. We'll read the data into our data frames from Pandas, and let me just plot the test side. So you can see here passenger ID, P class, name, there are different names, sex, male, female, age, and the different features which we just discussed. So data is the data frame which consists our training data set, and test is the test data set. So we're first checking if there are any null values in any column. So, okay. So passenger IDs has 0, survived as 0. Only age has around 177 missing values. So we'll have to fix that. And cabin has a surprising number of 687 missing values, while embarked has 2. The rest of the other features seem simple, and we'll try to fix them. So first, the main question is how many of the people survived? Of course, we know that 1,500 survived and out of 2,000, but let's just plot a small graph to analyze how many people survived. So this is a pie chart. Around 38% people survived, but 38% people survived and 68% people died, unfortunately. And this is the graph regarding that. Okay. So there are 891 passengers in the training set, but only 350 survived, and the total. Okay, so we need to dig down more to get better insights from the data and see which categories of passengers survived and who didn't. All right. So before we jump into all the feature engineering, let me just make clear the types of features which are available. So there are three major types of features in a data set. They can be categorical features, ordinal features, and nominal features, right? So categorical features mean that these are just names or strings, and there is no relation in between each of them. So maybe say different car names. Suppose if you take Toyota, they have a car called Camry, Corolla, Avalon, SUVs, and stuff like that. So when you give these, so all these names are in different rows of the same column, and it doesn't necessarily mean that Corolla is better than Camry or an Avalon is better than a Camry, because each of the cars has their own different uses and advantages. So there's no ordering of variables of the same type. So in this case, we can just have, okay, so these are called nominal variables, where the feature is essentially just the name and it doesn't have any data as such associated with it. It's just a label. Ordinal features, on the other hand, these are also labels, but these labels have a certain order of hierarchy. So for example, if we have a feature like height with values tall, medium, and short, then we can understand that short comes before medium, which comes before tall. So there's a certain ordering which makes sense. So why this is different from categorical features is because we can label them in such a way so that it starts making sense to the model. As in, we'll maybe label short as 0, medium as 1, and tall as 2. So there is a relation in between different different features of the same variable. So ordinal features in this data set is P class, which is the passenger class. There's a first class, second class, and third class. So the most used, like the easiest to understand for a model is a continuous feature. So a continuous feature essentially means that there are no discrete steps, there are no labels as such, and these are just continuous values. So age, for example, obviously. So let's start analyzing the features one by one now. So let's plot the sex feature and see how it is affecting our survival rate. So what this does is basically it counts the number of values in the male category and female category and plots them according to their survival. So we see here females who died is 81, whereas males who died is 468, which is a very stark difference, which means that sex is a very important parameter here. If you guys remember the movie, the the protocol which they followed was women and children first. So that is what is probably being reflected here. Um, all right. So let's plot this same data. This is a bit difficult to understand and analyze. It'll be better if you can see a graph. So, okay. So the difference is pretty stark. Sorry. Yeah. So yeah. So this the left graph represents the people difference between like the number of male and female people who have survived, and over here is count of the entire people, like all the males who survived and the males who died, along with the females who survived and the females who died. The red refers to the survived ones and the blue refers to the dead people. Okay, so the number of men on the ship is a lot more than the number of women. Still, the number of women saved is almost twice the number of males saved. The survival rate for a woman on a ship is around 75%. Uh, okay, around 75%, while that for men is 18 to 19%. So obviously, as I said, it looks like a very important feature for modeling, but we need to see all the other features as well. All right, so we're plotting out ordinal feature P class, and so this is what the plot looks like. This is a cross tab, which means that the lighter ones have lower values and the darker ones have higher values. So obviously you can see here the sum of all uh, survived and dead people is here. Total is 891, and in each class it's showing that in P class, P1 class, 80 people died, whereas from the third class, a lot more people, around 300 people died. So similarly for other classes, and we'll plot this data again and see how it looks like. So, all right. So number of passengers by P class. So you can see uh, the third class has a almost 500 people are there in the third class. In the first class there are few people, and in the second class there are fewer people. So plotting there the glass-wise data, but divided into survived and dead. So as you can see here, it's a very stark pattern that people in the third class died the most. Probably it might have to do with the overcrowdedness or the location where the iceberg gets struck. We don't know for sure. And as you can see, if you were from the first class, you had the best chance of surviving, because this graph is the highest for first class only, even though the number of passengers is not even comparable to the third class passengers. Almost the third class passengers almost more than double. So we clearly see that passengers P class were given higher priority while rescue, even though the number of passengers in P class were a lot higher. Still, the number of them surviving is very low, somewhere around 25% only. So around 63% of P1 people survived, while 48% died. 48% for P2 survived, sorry. All right, so let's plot this graph. This is the same data which we plotted here for the sex and survived conditions. All right, so okay, so the same data we are plotting here in terms of factor plot. Factor plot essentially is uh, a graph where the top part of the graph is joined by lines so that we can understand the difference or the gradient between different classes. So again, it's the same data, so we'll move ahead. We'll go to age, okay now. So let's see the overall like condition. Oldest passenger was of 80 years, youngest passenger was of 0.42 years, and the average age given is around 29 years on the ship. So it was a wide variety of age ranges. Let's see how that pans out. Uh, okay, so now we are using for continuous features is something called a violin plot. So let me explain what a violin plot is. So this is for different passenger classes, and this is for different. On the right is for different sex. So the line in between represents the uh, class, and the box in between represents the uh, middle quartile, and the white dot in between represents the median. So let me just scroll down for a second. I'll come back in between. So this is the anatomy of a violin plot, and the wavy lines you see on the side are the density plot, like they are the probability distribution for that class. So here the red probability distribution refers to whether they survived. So if you see the graph in a horizontal direction in this way, you can see that the peak is around people of age 35 to 40 who survived, and for dead people the peak is around 40 to 50 where the most people died, and so on. So you can analyze this plot, and the observations from the plot are as follows. The number of children increases with p class, so it means that the people in third class had more children, and the survival rate for passengers below age 10 looks to be good irrespective of p class, which we know from the movie is that uh, the women and children were given the first priority. So even if you are a poor child, it didn't matter if you had if you it didn't matter for them, they just saved you anyways. So survival chances for passengers aged 20 to 50 from p class 1 is high, and even better for women. So you see, so in the range 20 to 50 there's a quite a peak, and it seems like a lot of the entire women density distribution gets covered within this range. So that's good. So before, you remember, we saw that age had around 77 null values. Let me just take you there. Where was it? Yeah, here. So we see that age had around 177 uh, yeah, 177 null values. So we wanted to fix that, right? So let's get to it. Um, yep. But see, so it's not very straightforward. This. So what one way to do this would be to just replace the null values with the mean of the data set. But that doesn't make sense because there might be kids whose age we filled as a young adult age. So let's just read this. uh, to replace NaN values, we can assign them the mean age of data set. But the problem is there were many people with many different ages. As we saw, the highest age was 80 years and the youngest was 0.42 years. So we can't just assign a 4-year-old kid with the mean age that is 29 years. Is there any way to find out what age band does the passenger lie? So what we can do here is we can look at the name feature. So looking upon the feature, we can see that names have a salutation like Mr. or Mrs. Thus, we can assign the mean values of Mr. and Mrs. to respective groups. So we are kind of doing what is called binning here. So first, let's just extract the initials for different data sets. For both, I'm doing this for both and for training data set and test data set, because uh, we need to have the same kind of feature transformations we do on the training data set on the test data set as well, because they're going to be fit to the same model. Otherwise, the model will give an error saying that it doesn't understand what feature or what transformation we are referring to. So let's just plot the data. All right. So there are a lot of different initials: Captain, Colonel, Countess, Don, Doctor, Chonkir, Miss, Mr., Mrs. So Mrs. and Mr. are the most common ones, while Master refers to a young male child. So that is some, and rest of them are just like one or two instances of everything. So I don't. We can map them out to the same variable. So maybe Captain can refer captain is essentially, from here we can see it's a male adult, so it can be replaced with Mr. Miss and Mademoiselle and Madame refer to a lady, a adult lady, so we can map them to Miss or Mrs. So let's do that here. So we're replacing these exceptional as such titles with regular ones, which are Miss, Mr., Mrs., and Master. All right. Um, okay, we'll just skip this for now. It's just a plot as such. So we'll fill the nan ages right now, and uh, let's do that. So what we're doing here is people who have missing age is null, and have the initial Mr. We're filling them age of 33, and people who have age null and title of Mrs. are replaced with age 36, age null, and initial master is replaced by 5. Age null miss is replaced by 22, and age null and other is being replaced by age 46. So that's the general distribution that we are assigning. Moving on. So now we again check if there is any null values in the data set. So let's just run this. So it says false. So we have no null values left finally. So now we can plot another graph which will tell us, what will this graph tell us? So this graph will tell us the survival rate according to their age values. So it's binned them into different five classes of distance 5, 5, 5, and you can see that uh, people who died more are in the range 30 to 35, where a larger number of, like, the people who are from age 0 to 5 have survived, have a better chance of surviving. This height here is not because more people not because a larger percentage of this age range was survived, but it was because there were just a larger number of people in this age range from 20 to 35, and even if a smaller percentage of them was saved, what was happening is that the uh, overall number of people who survived was more than, if you say, this age range, or this age range also, the older people. So toddlers age 5 were saved in large numbers, women and child first policies, and the oldest passenger was saved. Over here you can see them, 80 years. Maximum number of deaths in the age group was 30 to 40. All right. Wow. So we are trying to plot the survived versus the P class. Again, we see here that irrespective of P class, Mrs., Miss, and Master were survived in large numbers. Cool. So embarked is kind of a not kind of an irrelevant feature, because it just shows that from uh, which port the passenger had boarded. I don't think that should have much of a difference, unless people from a certain class or a certain gender category boarded from a certain port, which is kind of unlikely. As you can see here, we plot the chance of survival by port embarkation. So it seems like from Southampton, a lot. So see, it's not starting from zero. So there is not a lot of difference between the survival rate and the embarked category, but whatever. All right, let's move on. Yeah. So this is a factor plot of the P class survived and the sex thing. So what we're basically doing is we're trying to see the relation between the gender of the people who boarded versus uh, the class they boarded, also in terms of the survival rate. And the column refers to the different graphs are for different boarding points. So you can see um, overall the number of males has always been low in terms of the survival rate, and it doesn't really matter from where you've boarded. if you're a woman, so you have higher chances of surviving. So filling the embarked NaN, what we're doing is we're just so there are just two missing values in the embarked category. So we're just filling them with S, which was the most common embarking destination. So embarked is null, false. So we can continue. Huh. All right. So another, can you please mute yourself, Abhinav?
Yeah.
Yeah. All right. So, so this CBSP, we saw that this represents whether a person is alone or with his family members. So let's just plot this. So we can see here a large number of people were at with one other person or with two other people, and then some people were alone, some people had three members, and some people had four members. So what we can see here, like as the family size is increasing, the chances of survival are decreasing. So what that relates in a more human sense means, it means that people who had their families with them, they had a lower chance of surviving, as in not all members of the family could maybe escape, like the parent, like the dad or the elder adults, male adults in the family were not able to escape. So the rest of the family also might have decided to stay with them and die. So pretty morbid, I know. All right. Let's go on. So the bar plot and factor plot show that a passenger is alone on board with no siblings. He has a 34% survival rate. The graph roughly decreases if the number of siblings increase. This makes sense. That is, if I have a family on board, I will try to save them instead of saving myself first. Surprisingly, the survival for families with 5 to 8 members is 0%, and stuff like that. So again, parent-child and parent-child relation, like how many children they had. One, it's the most common is one and two children the people had, and again we see somewhat not much difference between children of families. Uh, like the different number of children doesn't seem to make very stark difference, but there is some peaks on three and one. All right. All right. So fair. So fair is another continuous feature. We'll just go quickly through this now. So because we want to pay more attention to the interesting part, which is the modeling and the feature engineering part. The voting part. So this is just a distribution of fares. So there are very high fares in the P1 class, whereas the fares in the P2 class, and this is just distribution. I don't think. So there looks to be a large distribution of fares and passengers in first class, and this distribution goes on decreasing as the standards reduce. Also, this is continuous. We can convert into discrete values by using binning. Okay. So I think we've come to a conclusion about all the features that are available to us. So we'll just go through them once. Sex, the chance of survival for women is high. There is for P class, it's visible that a first class passenger had a more chance of survival, whereas P class for women, P class 3 was very low. For women, the chance of survival from P class 1 is almost 1 and is high too for those from P class 2. Children less than age 5 to 10 had a high chance of survival. People between the age 15 to 35 died a lot. So correlation between features. So what we're going to plot is called a heat map. So what a heat map essentially does is it plots the inter feature relationship. So we have a column. The left column is also passing the different features, and so is the bottom column. And this here is the legend we have. So uh, I'll explain to you how to interpret this plot. Okay. All right. So positive correlation. If an increase in feature A leads to an increase in feature B, then they are positively correlated. A value of 1 means a perfect positive correlation. So what that essentially means is that both of the features, if they have a positive correlation, it means that both of the features are encompassing the same information. So it doesn't it may be such a case that both their one of them is redundant. Maybe if we have a name, we don't need a separate column for first name and last name, because essentially it's just a name. It doesn't make that much of a difference. Negative correlation refers to when, like, inverse proportionality essentially, which means that if increase in feature A leads to decrease in feature B, then they are negatively correlated. A value of -1 means a perfect negative correlation. So now let's say two features are perfectly correlated. That's what I told. So this means that both features contain highly similar information and there is very little or no variance in the information. This is known as multicollinearity, as both of them contains the same information. This is a technical term you might want to remember. So do you think we should use both of them, as one of them might be redundant? While making or training models, we should try to eliminate redundant features as it reduces training time and many such advantages. So, all right. Now the feature engineering part. So this will be quick because there is not a lot of feature transformations that this dataset will be requiring. So we'll just get on with it quickly. So as I explained before, feature engineering essentially means making your features you get such that the machine learning model understands them better rather than us understanding them as humans. So we'll create a new column called family size and alone. So we know that the uh, PRCH feature and the SIBSP feature relate to the number of family members a person has. So we'll extract features from them. We'll add the parent-child feature to the sibling spouse feature and create a new one called family size. Let's just process that and plot that. Okay. I think that error is due to um, just a second. Um, yeah, there we go. So, oh, so the cells which didn't run. Hello, hello. We'll just run these. We didn't run these because there was some selection error. It was running only the characters I had selected. So I'll just run these. So you can view this notebook later. I'll provide you the link in on the chat, on the YouTube chat later, along with other discussion resources. So okay, let's go back. Okay, where were we? Feature engineering. So yeah, we created a family size which adds your parent, child, and your sibling SP, and we're plotting them. So again, it shows that we saw this before. Family size 3 means higher survival rate, suddenly drops at 4 and rises at 6. Kind of weird, I know, but that's what the data is. And the survived rate. So it is more like very high chance that you survive if you were yeah, so family size 0 means the passengers alone. Clearly, if you're alone or family size 0, then chances for survival are very low. So here, whereas these are people who have families. This also looks to be a very important feature in the model because suddenly there's a drop. There's a very distinctive pattern. It's not just like a flat line curve or such. All right. This is another factor plot for alone and survival with respect to different classes. So don't worry if you're not able to like understand everything I'm saying right now. I'll provide the link to the notebook in the description, so you can go through it in your own time as well. So feature range we said is a continuous feature, but we are binning them into certain parameters, because what was happening on the above graph we saw when we plotted the distributions of features was that even in first class there was a wide range of fares people had paid. So it makes more sense to group them in groups of 4. So pd.qcut does exactly that. It defines ranges and cuts the data into 4 equal bins basically. So let's just quickly finish this off. Then we're labeling the fare categories is what we're doing here. So 0 to 7.791 is 0 label, 1 label, 2 label, and 3 label, and so on. So let's do that. Okay. So converting strings to numeric. So we cannot pass strings to a machine learning model. We need to convert features like sex, embarked to numerical features. So male, female is replaced by 0, 1. Embarked is replaced by 0, 1, 2. And Mr., Miss, Master, and other is replaced as 0, 1, 2, 3. Now we'll be dropping some unneeded features and we'll plot them. We'll plot our final heat map. So these are the more features we have retained. Some of them are features which we generated and some of them are features which were given to us. So now the interesting part, predictive modeling. So obviously there are a lot of ML models available on scikit-learn, logistic regression, support vector machines, random forest, k-nearest neighbors. So having to discuss all of them in depth is beyond the scope of today's talk. But I highly recommend you to understand how each of these models work and only have intuition on what the model is doing, so you can change the parameters which different models have based on your understanding of them. So for now, we'll just be applying them to the entire data set we have and seeing our results. We're importing all these. This is a useful class called train test split. Given a data set and given a test size, it will split the data set into its it'll basically generate a validation set and a training set. So validation set is a part of the data set which was present in the training set, and we have the target features for it. So we'll train only on the subset of the entire training set called train. Kind of confusing, I know, but the validation set is a part of the training set which will act as our validation, our test set for now, uh, so that we can understand how well relatively models are doing to each other. Because you can't just keep on submitting to the leaderboard, keep on submitting, and because it's a long tedious process and it leads to a lot of wastage time. Instead, you can just test on your validation set and see your results and do whatever changes you have to make. So then we are creating our labels as a separate column. We'll pass them separately to our this thing. All right, we ran this already once. I guess what we'll do is we'll run. So it'll make more sense to us. And we'll run this as well. Okay. So radial support vector machines. So we'll not see, as I told, there's no time to understand each every model. So we'll just run these models and wait for them to run. So, okay. Accuracy for RBF SVM is 0.8. So 80% accuracy. Pretty good, I would say, for not doing much. SVM, linear SVM gives us 79% accuracy. Logistic regression gives us around 80% accuracy. So what we're doing here is we're defining a model. Here in this case, logistic regression, here SVC, and here SVC with RBF. And we're calling fit. So this fit method you have to pass at least two parameters, which is your training values and training labels. So the model fits to it, and then you can call a predict function and pass it the test parameters. And basically you'll get a prediction in a column here. And then what we're doing here is we have a prediction and we have our text underscore y, test underscore y, which is the correct labels for the current predictions. So we pass it through the accuracy score function from metrics, scalar metrics, and this is our predictions, and this is our y. So we'll return what percentage of our predictions are actually matching with our true values. So next, we'll have a decision tree uh, around 78%. So all the good thing about sklearn is all the models have the same format, like a fit method and a predict method, and you can use the accuracy score for almost any set of lists you have, provided the lengths are same. All right. So what we're doing here is we can change the number of neighbors attribute in KNN, right? So we are going through a list of like we're setting 0, 1, 2, 3, 4, 5, 6, and creating a model for each parameter. So and we are plotting out the accuracies. So you can see here when we had one neighbor, we got a 66% accuracy, and the accuracy is kind of increasing and then plateauing or slightly decreasing as we reach around say 5 or 6 in. So the maximum value was 79% accuracy, which is still lower than our uh, few other models that we checked out. All right. Moving ahead, Gaussian naive Bayes and random forests. 77% accuracy is not great, and 78% accuracy is from random forest. Okay. So another important thing here is the accuracy of the model. Not the only parameter that we can understand a classifier by. So what happens many times is we saw an accuracy of 80%, right? So now this seems to be a very good accuracy for a classifier, but can we confirm that it'll be 80% all for all new test sets that come over? The answer is no, because we cannot predict or determine which all instances the classifier uses to train itself. We're just feeding it the data and we get an output. As the training and testing data changes, the accuracy also changes. It may increase or decrease. So this fluctuation in accuracy is known as model variance. So to overcome this and have a more generalized model, not have a model overfit on a certain data set, uh, we can use a technique called cross validation. So let me just explain. So uh, so many times the data is imbalanced. That is, there may be a large number of class one instances, but less number of other class instances. And it might happen that the class one instances which are high in number are present in the training set, but very few are present in the test set. So that will it will reduce the accuracy of our classifier, obviously. So k-fold cross validation works by dividing the data sets into k subsets. So it divides itself into k different parts, and in each part. So out of the k parts, k minus one act as a training set, and one of them is reserved as a testing set. And this process is continued multiple times, such that at every subset is at least once used as a testing set, and then the accuracies and errors are averaged to understand the robustness of the algorithm. So there are modules for from sklearn to do the same for us, and so what we're doing here is we're importing all those cross validation algorithms, and we are creating a list of our classifier names, and we are uh, passing them through a for loop and creating a cross validation through each. So this cross val score essentially runs a cross validation algorithm. You can define the number of folds you want and the type of scoring you want and your model and your training and testing data. So it is all inclusive. You just have to pass these parameters and you'll get a result. So we defined number of splits here as 10 and a random state of 22. That doesn't matter. It's just in place to uh, ensure some degree of generality. It introduces an extra generality parameter. So on plotting these, we see that the cross-validation mean of radial SVM is high, 0.804, and for decision trees 0.800. All right. So we'll plot these in a graph. So almost all of them are same, But mind you, in data science, it very much happens, especially in competitions, that a small accuracy difference can mean your rank jumping from, say, 500 to 200. So you should not ignore any thing. So again, we'll plot a confusion matrix for our models. Confusion matrix essentially is the plot of our, like, it defines the success of our model. So the column called actually positive and actually negative represents the true values in the data set, and predicted positive and predicted negative represent the predicted values in the data set. So what we want for our model is that the left diagonal, true positives and true negatives, should be high as compared to the false negatives and false positives. False negatives means that we predicted it to be false, but it was actually true. And false positive means that we predicted it to be true, but it was actually a negative class. So that's what it is. So we'll plot the confusion matrices for the models we trained above. And this is what I explained, the interpreting the confusion matrix. So yeah, here's the plot. So we're having approximately the same number of false positive, false negatives, because 103, 13, 110, 121, etc., etc. This is for our reference. Okay, now the final part. This is kind of advanced. So ensembling, what happens is, now we saw that different models are giving a different accuracy, but that, so due to the architecture of different models, it doesn't mean that, like, different models may be extra learning their predictions from different parts of the data. So that depends on the architecture and the algorithm which the models are based on. So a good way to encapsulate all the types of analysis is to combine all the models into one. So it's kind of confusing. So how do you combine all models into one? Isn't there a reason why they're different in the first place? So what we can do this, we can have a consensus based algorithm. So this is called ensembling. What it means is that we will have predictions from all algorithms, and we'll take the average of all the predictions, and then we'll find the predictions saying, and that will act as our final predictions. So there are different ways of doing this. First is the voting classifier. It is the simplest way of combining predictions from different simple machine learning models. It gives an average prediction result based on prediction of all the submodels. The submodels or the base models are all of different types. So as I told you, you pass a list of different estimators in the voting classifier class, and it will give you the average for the an ensemble model. So basically, every model gets an equal vote in this case. There is another class where you can vote, like you can give certain models higher preference, say suppose high preference or lower preference. So suppose you train a model which has a pretty low accuracy, uh, you wouldn't want that to have a very high say in what your prediction is. So you can uh, reduce the, what do you say, the voting rights as such the model has. So we'll just run this and see what the results are. So still not a very great improvement, around 80%, same as the, but it is at least as good as the best model. So bagging is another general ensemble methods, but it is different from voting classifier in the sense that it works by applying similar classifiers on small particles. So in the previous voting classifier, we passed different kinds of estimators like logistic regression, Gaussian knife base, and ran them multiple times. But instead, we'll be dividing the data set here in different parts, and we'll be running the same type of classifier, say KNN. If you choose KNN, we'll just run KNN on different parts of the data set and average their predictions. So we just go through this quickly. I think we're close to running out of time. So back KNN. So back classifier, you pass a base estimator as KNN and number of neighbors is 3, getting an accuracy around 80%. A back decision tree, let's see how much we're getting here. All right, it's taking its time. So okay, not a great accuracy, 78%, and the cross-validated score is better, which means our model is more generalized. All right. let's move on. Boosted iterated learning. So boosting is essentially a technique which uses sequential learning of classifiers. So what it does, it iterates through the dataset very much like a machine learning, like a neural network. And what it does, what it does is it analyzes after every iteration that uh, so which features it got wrong, which instances, and the features which it got wrong, and then it will improve them. It will give more weightage to them, and the tree branches in their direction as such. If you know what a boosted tree is. So at first the model is trained on complete data set. Now the model would get some instances right while some wrong. Now in the next iteration, the learner will focus more on wrongly predicted instances or give more weight to it. Thus, it will try to predict the wrong instance correctly. Now this iterative process is continuous and new classifiers are added to the model until the limit is reached on accuracy. Makes sense. So there are different models: AdaBoost, stochastic gradient boosting, and XGBoost. So these are all different algorithms, and we'll see how they're performing. Okay, so cross-validated score is around 79%, still not our best. Cross-validated score for gradient boosting is 80. All right, and XGBoost has giving a accuracy of 79. So we're almost done, but let's just see. Yeah, so regarding boosting, there is a YouTube channel called StatQuest, and they have a very clear tutorial series on different uh, statistic based learning. Like I learned my boosting algorithms from there, so I recommend you check it out. You'll understand these terms better then, I guess. It would make more much sense otherwise. So I guess we are done with all the predictions. Now let's make a submission. Interesting. So we what you can do is you can choose one model. Like I'm choosing the ensemble linear RBF, and passing my test values as the parameters. Now this comes from the test data set directly. All right, this is not our validation set. This is a test set, and I'm creating a final submission array for that. And in the sample submission, I'm replacing the survived column with the final submission. So the sample submission essentially has the passenger IDs in one column. Let me just show it to you. So sample submission. So it has a passenger ID and survived class. So I'm replacing my predictions with the survived class, and then we can just submit this. So now this data frame sample submission will convert it into a CSV, and we'll upload it to the Kaggle contest page. Wow. So I've already done that here. And we'll see our model. So this is what the notebook looks like when it is published. You can get a nice HTML based thing and people can read your stuff. Let's go to the output column, and we now have our submission.csv file. And I can just click submit to competition. Yes. All right. So, okay, our submission is complete and we've scored around 77% uh, on the competition, which is not good, not bad for our first submission. So I guess we're done here. We'll go back to the PPT now. So this was the Titanic challenge. I hope you liked it. So a few useful resources to begin your Kaggle journey as such are, there's a really good course on Coursera called How to Win a Kaggle Competition. And I personally love Kaggle's Medium blog. They interview winners of each competition after they're done, and they discuss their modeling techniques and different data processing techniques and stuff like that. And there's a Kaggle notebook section, different notebooks, people with different approaches, people discussing a lot of stuff. And so that is a very useful resource. As I told, YouTube StatQuest is a very important resource. Don't worry, I think it'll be uploaded on YouTube after we're done, so you can view the talk later as well. Okay. Okay, this is a bit of a motivational slide where you will. So how you should approach Kaggle. So Kaggle is not a very quick validation providing software, like a platform. What am I saying? Okay. So what happens is many of the competitions run for months together. So, and if you stop improving your model at some point, you are definitely going to be overtaken. So there are 2 months for this competition to go, and 500 teams. Some competition is going on for 9 months, and this competition. So this competition is one of the most featured competitions. It has a $1 million prize, and this has been going on from the last 4 months, if I'm not wrong. So you have to persist a lot. Like you have to keep learning. You have to learn from others, explore things. People implement a lot of research papers on their own and apply them to the data sets. It's a very like a very normal thing to do. And when you learn things, you can apply them in your models, improve your score, and the entire process has to be reiterated. The learn apply has to be reiterated over and over again until the competition gets over. So I think that's the only like tip to success. The resources, I will be providing the uh, notebook which I showed to you, which I ran. You can copy it and you can change a few things. You can try different classifiers, try different types of feature processing, data processing, and see what suits you, what improves your score more, improve your position in the leaderboard. And as I said, keep doing that, keep learning, keep applying, and persist at your competition. I am sure that everybody has the ability to be a really good Kaggle competitor. I'll be more than happy to connect with you guys on LinkedIn and Kaggle. These are the only two social media sites as I'm active on as of now. On GitHub, I have the same username. Maybe you can follow me there. Thank you. It has been a great pleasure to give this webinar, and I hope I wish you all the best. Thank you. Yes, the YouTube channel is called StatQuest. I'll provide all the resources as a link, as a set of links later.